this.
Hi, the AI assistant.
Okay.
While he's doing that, this you don't have to point. It's just it has something on there. So if you just move,
Oh,
the,
okay, I see.
that takes a little bit of getting used to. Maybe better to look at the screen when you're doing.
Okay. Thank you very much. So, hello everyone. Today I would like to introduce GenCReM, the novo design guided by explainable docking. So very briefly about motivation, as it was already mentioned in the previous talk, the available theoretical chemical space of drug-like molecules are huge. It's larger than the number of stars in the universe. And the process of heat finding, sorry. Oh yeah, sorry. So thank you. And the process of heat finding can be compared actually with looking for a needle in an astronomically large haystack. And how we can find our needle in such a space. What method we can use? Yes, we always can use some screening of pre-enumerated libraries, but we always will be limited by them, right? So there could be some potential problems with novelty. The more interesting for us approach is actually de novo exploration. So to actually take a look onto this huge available space, but as I mentioned, it's so large, so we cannot physically exhaustively screen it. So what we need some efficient and goal-driven exploration. It was already also mentioned that it's not enough just synthesize, or it's not enough just generate some molecules, right? We need to synthesize them, and to evaluate how easy it is to synthesize a molecule, we are using synthetic accessibility score, which was introduced by Peter Ertel. The SS score can return value from 1 to 10, where 1 stands from the very easy to synthesize molecules and 10 for the hard to synthesize. So there's a distribution of a Kimball, and there's also example from the Kimball with the SS scores. To address the mentioned before limitation and issues, we actually introduce the GenCReM, where we try to combine the CREM, the novo structure generation framework, which by design returns you always chemically valid molecules, and genetics algorithm for the genetic algorithm for the navigating chemical space efficiently. So a little bit about CREM. So CREM stands for chemically reasonable mutation, and it was introduced by our supervisor 5 years ago. So it's a fragment-based method, and the idea is very simple. So you have your database. It can be from Campbell or enamine, or it can be even a local database with molecules. So, and all molecules, they're just cutted exhaustively by the all single bonds. So you have fragments, and the algorithm store these fragments as well as their context. So the attachment around attachment points, we are saving the context, the environment of this attachment point, and to mutate a molecule, we also fragment it. And if in the database we can see another fragments, but with the same environment, with the same context, it means that such fragments are interchangeable. So we can easily replace them. So it can return a very large number of new molecules, but it's always chemically valid. Another interesting feature of the approach that we can actually even use for this, to derive this fragment database, we can use the custom like in-house libraries. So we, by using these molecules, it contains some fragments or some chemistry, which are most used in this like particular group of chemists. So we, the resulted molecules will be even more synthetically accessible for these specific groups of chemists. So also on Friday, there will be tutorial about GenCReM, so very interesting one. So everybody welcome who are interested about this topic. And as for genetic algorithm is an optimization method which was inspired by the biological evolution. So we are using such term as population mutation crossover. And in our case, we are using, as a population, we are using molecules, RD-kit molecules. Yeah, the size of population can be varied, like from the beginning, it's preset parameter. So we have our molecules, then we mutate or crossover them, and then we evaluate new generated molecules by the fitness function. So far, we introduced docking score, ligand-protein interaction, similarity, and score and the RMSD, but it can be easily expanded to any other terms. I would like to notice that we are not using SS score explicitly. We'd rather, like, spoiler alert, we are showing in our study that we can control it indirectly by just changing GenCReM parameters. So it's not used in the fitness function of the molecules. And to normalize these terms, we are using softmax function. And then we evaluate our new molecules, children molecules, and we need to select the molecules which will go for the next iteration. And for this, we are using survival mode. So we mix together the children molecule and the parents ones, and then we select n molecules with some probability. So the probability based on a fitness value of each molecule, but none of the molecules has a 0 probability to be chosen, right? And this procedure is continued like multiple times until the maximum number of iteration is reached. Or we also introduce the stagnation criteria when we see that there is more than 90% of the previously seen molecules were generated. So like more than 90% of duplicates, which were already seen in the previous iterations, and it's continuous for more than 5 iterations. We just stop our run prematurely because it means that we probably already like stuck in the local space, or we already explored what we can nearby. A little bit more details about mutation and crossover procedure, how we are doing it actually. So for mutation procedure, we are using GenCReM. And yeah, we are using external database, for example, Campbell enamine. And but we theoretically we can replace any atom, any fragment, but we decided that it would be nice actually to keep important atoms. And for this, we introduced the atom contribution procedure. So how we are doing it? It's a right. Okay. It's a right side of the slide. So, and it's done for each molecule. So first of all, we run a regular docking procedure. Yeah, we have our docking score baseline, and then we iteratively, atom by atom, replace each atom to the non-polar hydrogen. And in this case, Vina and Gnina, they're just ignoring such atom. They're like take it off into the not taking it into the account. And after we masked our atom by hydrogen, like a heteroatom, we calculate the difference. We calculate, we rescore this molecule with this hidden atom. And we calculate the difference between the baseline docking score and this docking score with the hidden atom. So we are doing it iteratively for each atom. And like this, we are getting like atom contribution for each atom. It can be negative, it can be positive, depends if we improve or worsen our docking score. And then we protect our key atoms. And by the threshold of the atom contribution, I will show more details, like what threshold that we are using and how we chose it. So I hope that it was understandable, the procedure, how we are doing it. And then, yes, and so in CReM, we are protect such important for the docking score atoms from the replacement. And for the crossover procedure, we are as well using CReM, but instead of external database, we are using some internal database. We are generating a database of fragments, which we've seen already in the previous iterations. And we also rank our fragments on the sum of the atom contribution. And then with more high probability, we are choosing the fragments which are particularly beneficial for this specific binding site. To validate our approach, we used the CDK2 target to BTR, and we decided to run a local chemical space exploration task or lead optimization. So as a seed molecule, we used co-crystallized ligand, CDK2 inhibitor, with 100 nanomolar activity. And it is known from the literature that for the activity, it is important to preserve the contacts between ligand and the hinge region. We wanted also that our molecule, like generated molecule, would have this contact. So we decided to protect these atoms which are involved into the bonding with the hinge region from the replacement. So like the white, as you can see, that this molecule, so some parts are white, some parts are colorful. So the colorful part is protected because it's involved in the bond. And the white part can be replaced in all our runs. And so, and also all output molecules would have this fragment. This just example of atom contribution, how it look like. So we ran this procedure for this input seed molecule. And you can see that there is some highly important atoms. So we actually, for GNINA, we used the protection threshold 0.3, how we chose it. So we actually ran the atom contribution calculation for another data sets. We took a look on the distribution of the atom contributions. They were from negative to positive. And we also visually took a look into the sum of these systems. And we wanted our threshold would protect not not large number or like small number of atoms, which are indeed somehow, so we try to see it visually that somehow it would correspond with the binding. And by this analysis, like empirically, we chose 0.3 for GNINA. For VINA, there was another threshold. So for each docking program, we need to like choose like threshold separately. Our criteria for the protection for the protecting of atom is that atom contribution value is larger or equal than 0.3, or the atom is a hydrogen actually, which involved in a hydrogen bonding. So we would like also to keep it. And in this case, for this example, you can see that there would be like 4 hetero atoms would be protected, as well as 2 hydrogen. And it's very nice that 2 of them, as well as hydrogen, are actually indeed important for the activity for the hinge region. So it's nice that like docking itself could distinguish it. Very briefly about overview what has been done yet. So in our in further analysis or in further results which I'll show, we used different radius. What radius stands for? So it's actually the size of the context which are take into account for the our interchangeable fragments. So the larger the context, the larger is environment, the more strict rules in a way we are applying. So it returns like less number of output molecules, but they're usually more synthetically accessible. And the opposite, for example, for radius 3, for a little bit smaller than 5 context, it usually returns much larger number of new molecules, but they're sometimes not really easily synthetically accessible. And we also run 3 types of scenario, low, medium, and high budget. So low stands for the 10 molecules in the population. So the maximum 2,000 of molecules were generated overall and docked. The medium stands for 100 molecules in the population. So maximum 20,000 docking events and 20,000 new molecules were generated, and high budget 500 molecules in the population. So maximum 100,000 new molecules were generated. So, and we are used, I'm showing only the results for Nina. We ran the same analysis and the same study for Vina, but we had problems that Vina couldn't reproduce the crystallographical pose from the beginning, so we decided to stick to the Nina. And there's also settings which were the same for all runs. So the maximum size of the replacement fragment cannot be more than 10 atoms. We also strictly filter out the molecules which was like not in the specific rank of the some physicochemical properties, for example, molecular weight less or equals than 450 and so on. All runs were replicated 3 times because genetic algorithm is a stochastic algorithm. So, and the best replica by docking score was used for the further analysis. And we haven't still validated and check our crossover procedure because we have some technical problems. It takes so long time to fragmentize all molecules on each iteration. So it's like for future, plans for future. And so as for results, we are starting from a low budget structure generation scenario. So you can see that there is number of iteration on the X axis, and on the Y there is a docking score. So the red color stands for the genetic algorithms with contribution, with atom contribution guidance, and the blue one for the regular genetic algorithm. The same, everything the same, just we turn off our contribution, atom contribution. So, and the line stands, the red and blue line stands for the mean docking per each iteration, like for all generated molecules per each iteration. And the shadow stands for the for the maximum and minimum of docking score from the generated compounds on this particular iteration. So, and what we can see? Well, we generated just 2,000 molecules, and we already could improve our docking score from 6 to almost 9, which is quite impressive with the atom contributions. So as you can see, the maximum on the I forgot, like somewhere here, the maximum is almost reaching 9, which is nice. Also, as we can see that red line, so we by introducing the atom contribution, we indeed can navigate through the chemical space more efficiently in a way, because we are like meeting more and more promising by docking score, of course, molecules, then we just using the genetic algorithm. So the convergency that atom, so we can tell that atom contribution helps the algorithm to converge early. And so maybe it would just require like more iteration, you know, for the regular genetic algorithm. So then we tried, so it was the results for radius free, as I told, like more loose in a way rules for the choosing the fragment. And now the more strict rules, so context 5 atoms, so less molecules, but a higher synthetic accessibility rate, easy synthetic accessibility rate. And in this case, we can see that atom contribution already don't, like the impact is negligible. Maybe because that that our chemical space become actually like much smaller, because we generate much less molecules, so it's already doesn't matter by which method we are doing it. Then we also try to apply the same procedure, but for the medium and high budget scenario, as I mentioned, like 20,000 and 100,000 generated molecules. And as we can see that we still can see that atom contribution helps algorithm to converge early, but it sometimes result that yes, the converge urging or early. And for the high budget, for example, for the high budget scenario, we already see that there is not much difference for the beginning, at least. That it's converged early and it's went to the plateau, and then it stopped actually prematurely because it's explored the local space already. But genetic algorithm without the contribution continue found even better hits, and it's because that genetic algorithm work much better with the larger population, with a much more molecules. But as you can see, for the low budget scenario, where there's only 2,000 docking events, we indeed can much improve our convergency and our results pretty much. Also, as I mentioned, it is important for the activity of the such inhibitors to preserve the contact with the hinge region. So we also evaluated what percent of generated molecules actually preserved at least one contact with the hinge region. So we were not controlling it explicitly. We can, but we didn't in this case. And you can see that atom contributions actually help to partially preserve important for the binding protein ligand contacts, which is pretty nice. And this, we just wanted to compare the distribution of a top 100 generated molecules for each scenario, for each radius, and also to compare it with the already known inhibitors with distribution of docking score of already known inhibitors from Campbell. And you can see that, yeah, like in all cases, we could improve somehow docking. But more interesting that even by running 2,000 dockings and 2,000 we generated just 2,000 molecules, and we already could reach like a little bit worse, but similar results as for high budget for the maximum molecules, which is quite nice. This when we introduce atom contribution, which we don't introduce, so the results like worse. And these examples of the generated molecules with the GNINA and SA scores. So you can just take a look how they look like. And we also wanted to see is it what about synthetic accessibility of the generated molecules, and also to compare it with the novel inhibitors. So we can see that actually it doesn't matter low budget, medium budget, or high budget, or it doesn't in a way matter if we use a atom contribution or not. They're like the same distribution of ESA score, but we can control our ESA scores, the synthetic accessibility of our generated molecules by the radius, actually. It was already shown in the article, and it's again, we see it by our results that we can control the synthetic accessibility of the molecules by just controlling the radius, but not by the parameters of the algorithm itself. I see. It's two slides, Astals. Yeah, thank you. So this also we wanted to compare it with the chemical space. With the chemical space of known inhibitors. So the blue stands, the blue dot stands for the known inhibitors. We run low budget as well, radius free, and the dot stands for the not including atom contribution, and the triangles stands for the including atom contribution. And you can see that we started from the 1 point, but then the exploration of chemical space that dots the molecules start separating with the iterations. And at the end, we have completely different clusters for the atom contribution and not atom contribution approaches. And by the color, we can see also that atom contribution, we could find actually more beneficial chemical space. You see that there is more like red, yellow colors than, and for example, for the not atom contribution, there is like mostly blue or green. Within the same number of iterations. So I will skip this. And as for conclusion, the combination of the GenCReM and genetic algorithm allows to merge synthetically feasible structure generation with efficient goal-driven chemical space exploration. Generation guided by atom contribution improve the most significantly low budget exploration, but also in some extent it helps to converge faster for the medium and large budget scenario. And synthetic accessibility depends only on the chosen context radius and is not sensitive to other settings. And I would like to thank the Dr. Koyes for his guidance and support with Nina. And also, I asked ChatGPT to actually tell how it sees the complexity of drug discovery, and it told that it can compare it if a person would have 1 million of puzzles, and the person needs to assemble it, but there is no reference picture. So, and it's generated this nice picture for you. So there is a GitHub link to our group. So there are very nice tools such as StreamMD for high throughput molecular dynamics simulation, EasyDoc for high throughput docking, and so on. So thank you for your attention.
We need to share.
Yes.
So first, don't forget the questions on Discord. I think, Anna, you have actually a few, so if you can answer them. Okay, so a few short questions. Yes?
So the structures which we found.
What is the protonation state there?
It's 75.
Amino that could not simultaneously protonate in that case. So what is your approach to it?
We are using mold GPK for this. It was already mentioned. Yeah. The question was what the protonation, because there is a molecule which can be protonate differently with the same probability. So which protonation we actually used. So we are just using the automatic procedure of protonation by mold GPK. And yes, it can sometimes make mistakes, that's true. So it's up to user to check the results, but it's still, as it was shown in the like previous EasyDoc talk, that it's still shows some correlation with the chemaxon. And we also, that my colleagues, they introduced some fixes. So we are working on it. So the like that protonation, yes, the protonation is very important, and I agree with this. Thank you for your question.
Then let's thank Aleksandra again.
Sure.